last time, by accident, I found myself making the traditional sketch of the refrigerator or refrigeration machine, which is the same as the heat engine, but it runs in the opposite direction in time. That is, the fluid packet is moving in the opposite sense. The traditional drawing, and I have to be very careful because I want to make another drawing here, is like this. The refrigerator requires power. I'm doing this sketch on a per unit time basis, which means steady state. It's a closed system operating in cycles. It extracts a rate of heat transfer called Q dot L, also known as refrigeration load, from a low temperature called TL, and rejects the sum of these two streams of energy as a heat transfer to a higher temperature, which is the ambient. We used to call it TH. Now we call it T0 because that's another name for where we are. So the QH or Q dot 0 is here. There was a homework problem that I assigned in which I asked you to calculate the entropy generation rate in this inside this closed system that operates in the steady state. It's a trick question because clearly, if this is the system, then the entropy generation rate in that box, here's the box, is Q dot 0 divided by T0 minus Q dot L, is the other way around, minus plus Q dot L divided by TL. Now, it's a trick question because clearly, this thing here is not the same as the lost power divided by the ambient temperature. Lost power being the sum of these two things. Actually, lost power is Q dot 0 minus Q dot L. You see? So, this should be a hint that, and we know the reason why this is a mistake. You'll see it again very soon. But this puzzle should be a hint that the drawing is wrong. The drawing is wrong because, as I pointed out last time, this arrow Q0 cannot flow to T0 unless this edge of the system is actually warmer than the ambient. And that's how you begin to respect a lot more those people who made the contrivance, in this case the household refrigerator. The back of the refrigerator is warmer than the air in the kitchen, and you should be able to shout to yourself, aha, meaning bad drawing, okay? Now, the drawing that appeared several times in this course, especially during the last two lectures, is that of the hardware associated with the refrigerator called the vapor compression cycle. In this contrivance, there is a compressor that requires power, usually called W sub C. The compressor compresses vapor selected or collected from a pot that on Earth, which is G here, separates saturated liquid from vapor, and the compressed stream is, so we have low pressure here, high pressure here. The compressed stream is dumped into the pot, but before that happens, and here is now T0, the compressed stream is cooled to ambient temperature. And the pot, also known as the evaporator, is so cold that it draws this heat transfer arrow. I had put state 1 here, which is the same as state 1 here, meaning F is state, G is state 1. The compressed vapor is compressed to state 2. It is then cooled to state 3. And then between 3 and 4, the compressed stream is throttled from high pressure to low pressure. And so we have regenerated this particular drawing by putting more details inside the so-called box. What was in the square box before is now in this entire drawing. You see the W dot coming in. You see the heat rejection rate to the ambient. You see the refrigeration load coming in. Okay? And we've already made a correction that what was missing in the simplest drawing, because the simplest drawing was a copycat version of the heat engine. What was missing was the origin of this refrigeration load. In the case of a refrigerator, which sits on the landscape called your home, this heat transfer rate originates from the ambient. It's called a heat leak, facilitated, quote unquote, by an imperfect insulation. So what was neglected was the insulation. In other words, contrary to the doctrine, the refrigeration machine sketched here is incomplete. So refrigeration machine, so the, let's call it the machine. By the way, you know what machine means, don't you? Who knows what machine means? Machine doesn't mean automobile. In Italy, they call it la macchina, or the French say la machine. They say voiture, never mind them. The macchina, you know. That's the correct name for it, but the machina is also my shirt. The word machine is Greek. It means contrivance, trick, let's say a human-made add-on. This is the definition of it. A human-made, see how general it is. A human-made add-on that enhances the effect of naked power, human power. So each of us is not the naked body you see in the anatomy book. That sort of a specimen went extinct before the adoption of fire. These are, did I tell you this already? Those of us, all of us, became much more powerful than the original Homo sapiens in very clear steps of advancement. One was, the first add-on was fire. the second was clothing, and the third was boating. Every single one had to do with power. So this, more primitive than primitive individual became more and more capable of moving on the surface of the earth. And the fact that, Egyptians and after did all these things, all the way to, written language and science today is, it's impressive, but it's nothing new. It's just the most recent steps up a very, very tall ladder. Okay, so machine, it's called mihani in Greek, means contrivance. So the machine, in this case, is two parts. The so-called cycle, also known as the closed system, and the insulation, which, let me now pretend that I'm a biologist, which I'm not. This duo in biology is called animal and niche. Okay? To have one that moves, you need the other. That, this is also known as the immediate environment or surroundings. And the machine, of course, is the whole, the entirety. All right? And according to your homework problem, if you're interested in checking the validity of the Guis-Todola theorem, which states that the lost power is equal to the total entropy generation rate times the temperature where the system rejects heat. This is the definition of, the source of this general result. Then you discover that the whole is in fact respecting the Guis-Todola theorem, because the total entropy generation is equal to, obviously Q dot L came from here, and that means this is Q dot 0 rejected to T0. So take notes, because I'm going to write something I have not written before. So, and then Q dot 0 divided by T0 minus Q dot L divided by T0, which of course is the same as W dot lost divided by T0. But that's not the point, okay? This is the total entropy generation rate. Then I subtract and add one term. This one, the one written here, the source of the trouble. So I say Q dot 0 over T0 minus the entropy stream that enters through the bottom, which is Q dot L over TL, and then plus Q dot L over TL minus Q dot L over T0. You can always steal 0 from me. You're welcome. Yeah. But the reason for the trick is that the first two terms represent the entropy generated by the so-called cycle. And the second two terms represent the entropy generated inside the insulation. You see, in the insulation, entropy out is QL over TL. Entropy in is QL over T0. So entropy generation in the insulation so entropy generation hold. This is what I wanted to bring you, to discover with you that entropy generation as a quantity, it is additive. Additive. This, by the way, this is a figure of a bad news. The currency that they would rather not pay. The other name for it is lost power. And this figure of lack of merit is the sum of the figures of lack of merit of the parts. Where else have you seen this, this sort of accounting happening? I did the comment already. You saw it in geometry. Here's the drawing, maybe the drawing of your house, or the wall of the house. It has many bricks. The volume of that wall is the sum of the sub-volumes. Same here. The size of the quantity of interest is this particular expression, which shows you, if you are to compare, as some people do, components, which one is more troublesome than the other, then go ahead and evaluate the irreversibility in one versus the irreversibility in the other.